The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Problem 9 states a small steel ball will float in a half full container of mercury when the water is added blank. So, they don't give us a lot, so you have to make a lot of, not necessarily assumptions, but you have to kind of use your own variables and try to figure out what's going on in this problem yourself. So, let's break it down. The ball's floating in mercury. So, below this line, we have mercury, and above it we have air. Nothing happening. Now, see something floating, generally, especially if you see something floating in a fluid, it should really make you think Archimedes' principle. Archimedes is the only guy that talks about floating stuff, and that's what we got here. So we're going to use Archimedes. Archimedes' principle is really just about static equilibrium in fluids. So this is really a force problem, just with some fancier ways of writing our force vectors. When you're dealing with fluids, best way to write your force vectors is always the rho GH term. So pulling downwards on this block is the weight, or on the ball is the weight. So the weight of this is just going to be our density of steel, because they told it was a steel ball, times gravity, times the height of the ball. So our diameter, let's just call it D. Okay. Pushing upwards on the ball is the buoyant force due to the mercury. We don't know what exactly it is. We don't know how far the ball is floating above it. So what I'm going to do is I'm just going to come up and say we have the density of mercury times gravity times some height h that the ball is submerged. So this is going to be our value of h. Okay? Doesn't matter what it is. Okay, you just need to know this is what the force vector pushing it up is, and this is what the force vector pushing it down is. Or the pressure vector, or however you want to think about it. So, second situation, they add water to it. So, same ball. This is going to be the instant after they add water to it, so before the ball actually has time to adjust or do whatever it's going to do. What we're going to do is we're going to look at how the forces are changed in this, and we're going to make a very, very educated guess about what's going to happen. So pulling down, nothing's changed. It still has a weight of gravity, density of the steel times gravity times the diameter of the ball, the height of the ball. Nothing's changed there. And if I'm looking at the very instance before anything happens, then the force due to the mercury hasn't changed either. With, of course, this being our h value. Nothing's changed. However, if we now, in this problem, have water filled to some point, doesn't matter what the point is, I'm just going to assume it's above it, because they said the container is half full. It doesn't really matter where you assume it. Anything's going to give you the right answer, right conceptual answer. We have a new force of water, a new buoyant force due to the water. So that value is just going to be the density of our water times gravity times this guy right here. This distance. So rather than coming up with a new variable, I'm just going to write in terms of things I've already expressed. So that's just going to be this diameter of the ball minus h. Okay? So, you can see it. Density of water times gravity times d minus h. Now, this seems like it's going to get really rough after this, but this is really the end of what you need to figure out in this problem. Basic concept is you have a weight pulling you down in both situations. You have a buoyant force due to mercury in both situations. When you add water, it adds another force, another buoyant force, which means it has a force pulling you up, pushing this object up. The water wants to get rid of this ball. It wants to settle down as low as it can and push the ball up. Okay? So if you have an additional force, okay, so now that the net force has changed, it's not quite equal to 0, it's going to move up a little bit. Okay, the water is actually going to pull the ball up a little bit. Some unknown amount that we don't know about, but also don't care about. Okay? Now, because of the fact that the water it's a steel ball inside of water, you know that it's not going to pull it up too much. Okay? It's going to cause it to rise slightly, which is actually going to be our correct answer. The ball will rise slightly. Now, just to recap the other answers, just to look at them, definitely should at least read all the other answers, even if you're very certain you have the right one. One of the other answers says the ball will float on the water. Now, this is a little intuition. Steel ball in water, probably not going to float. Okay, definitely not going to float. So, hopefully your intuition will tell you that answer is wrong right off the bat. The mercury will float on the water. Well, mercury's density is much greater than water. Mercury will never float on the water. So that's a wrong answer. The ball will sink to the bottom of the container. So I think what they're trying to do with this one is try to trick you in thinking that, the weight of the water is going to push the ball down, which I guess kind of logically makes sense, but with fluids, a lot of times the situations are counterintuitive. The best thing you can do with this fluids chapter is read those principles and make sure you know what happens. If you have something with water with any fluid around it, if it's got any fluid, it's all the way around it, partially around it, whatever, there is a buoyant force to the fluid. The fluid doesn't weigh it down, the fluid wants to push it up, which is the concept of the buoyant force. So adding water will not cause the ball to sink to the bottom of the container. Okay? The ball will lower slightly more into the mercury. And once again, we can look at our force vectors and we can just say, well, we added a force upwards. Why would the ball move downwards? The answer is it wouldn't. A new upward force would actually cause the ball to move upwards. So leads us to this conclusion because the other four can't be right, and we've proved that this one is right. And that's how you approach this conceptual problem.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.